Welcome to this video on Bayesian inference by hand. Today I'm going to be deriving the posterior distribution for a binomial random variable assuming a beta prior. So this video is aimed more towards an intermediate-ish audience. I'm not going to be explaining what exactly a prior or posterior distribution are. I'm going to be assuming those things because I'm assuming that if you're looking to derive them from scratch, you probably know what those things are. And this video itself will be probably a little bit lengthy, so I want to try to keep it under an hour long. So here I have a random variable x assuming a binomial distribution, and I have the parameter theta distributed as a beta distribution with two arbitrary parameters, alpha and beta. So let's go ahead and write the likelihood for x given our parameter theta, which is the binomial, and this is, as you probably already know, n choose x, theta to the x, 1 minus theta, n minus x. And then the prior, which is the beta distribution, p of theta, is gamma alpha plus beta over gamma of alpha times gamma of beta times theta of alpha minus 1, 1 minus theta, beta minus 1. So this is the PDF of a beta distribution, which I can, well, I already have it written right here, that's fine. And one thing to note, which will be really helpful for us, is that obviously this integrates to 1. And if we integrate with respect to theta, this whole gamma function is a constant. In fact, it's the normalizing constant, which makes it a PDF in the first place, right? So you can think that if I integrate, oh, that's a bad integral. If I integrate this from 0 to 1, alpha minus 1, 1 minus alpha, beta minus 1 with respect to theta, then obviously this will be equal to the reciprocal of this, because this is the normalizing constant. We have to divide by this gamma thing in order to make this 1. And so the integral of this form, of course, on the domain 0 to 1, this doesn't work for anything else. But if our domain is 0 to 1, which is all we care about in this case, then this is gamma alpha, gamma beta over gamma alpha plus beta. Because if you multiply these two things, that gives you 1. Alright, so it's very useful to use this identity here, which we're going to be doing in just a moment. So let me erase this. So as you probably already know, if you're familiar with Bayesian statistics, to get the posterior distribution, this is the probability of our parameter theta given our observed data. And using Bayes' theorem, this is the probability of our data given our parameter theta, which is the likelihood, times the probability of our parameter, divided by the marginal distribution of x. So if we integrate over theta of px given theta, this is essentially the compound distribution, or the marginal distribution for x. In other words, we take the joint density of x and, or of our likelihood and our prior, and to get the probability of x, this is marginalizing out theta. So if you're familiar with standard conditional probability, you should already be familiar with this, but some people write p of x, some people write the entire integral. Just for completion's sake, I'll just write the entire integral. Alright, so now we can actually compute some of these things. So let's first get the joint density, which is simply just the product of our likelihood and our prior. So if we keep the constants to the left, well, first let me write this expression. Px given theta times p of theta. This is simply n choose x gamma of alpha plus beta over gamma alpha gamma beta times, now note that we can combine these two terms. So we have theta x and theta alpha minus 1. Those have like bases, we can combine them, and this becomes theta of x plus alpha minus 1. And then again, we have a like base, 1 minus theta, so we can combine these two, and this becomes 1 minus theta to the n minus x plus beta minus 1. Excuse my poor handwriting. So now this is the joint density of x and theta, and also my other two hyperparameters, alpha and beta. And so now we want to normalize this, and so we have to, of course, integrate this, which at first you might think, like, wow, this integral looks extremely complicated, but actually it's not complicated, because see that this is a constant, and so really we're just integrating this, and using that identity I just showed you a minute or two ago, this actually becomes extremely straightforward to integrate. So let's do that real quick. The probability of x, in other words our marginal distribution, is, well, let's take out these constants first, and choose x gamma of alpha plus beta, gamma of alpha, gamma of beta, and now we have the integral over theta, which ranges from 0 to 1, and now we have theta to the x plus alpha minus 1, 1 minus theta to the n minus x plus beta minus 1 with respect to theta. Alright, so recall that if we take the reciprocal of this, this is the normalizing constant. In this case, alpha is just x plus alpha, right? Because if we have alpha minus 1, well, we have x plus alpha minus 1, so clearly x plus alpha is alpha in this case. So this equals, I don't have enough room, so let me try to go down here. So this equals, let me try to copy this piece so I don't have to write it again. Alright, copy that. Oh, whoops. I just want to copy this. Alright, there we go. One of these days I'll get it. Alright, so we got our constant and choose x, alpha, blah, blah, blah. And so now x plus alpha is alpha. So we have gamma of x plus alpha. And then we have n minus x plus beta minus 1. Because again, recall, this we have beta minus 1, and this is n minus x plus beta minus 1. And so clearly beta in this case is n minus x plus beta. N minus x plus beta. And then we just have the sum of these two, alpha plus beta. Well, the x's cancel out, and we have n plus alpha plus beta. So this is gamma of n plus alpha plus beta. And there you go, that's it. A very straightforward integral. And so this is p of x. And so now to get the posterior distribution, probability of theta given x, well, now we just divide these two. So we have the likelihood up here. In fact, let me try to copy these things so I can save some time. So we have our joint density. Joint density. And let's divide that. Divide that by our marginal density. I messed that up. Alright, it's much quicker than writing it out again. Alright, so this is our joint density, this is our marginal density. I just copied the same thing, didn't I? That's not what I meant. Why isn't this copying? Okay, give me just a second. Apparently I'm having technical difficulties trying to copy this thing. Okay, there we go. Okay, my bad. So, joint density, marginal density, we divide them. Notice that immediately this cancels out, and this cancels out. There are some things missing here. Clearly this copying pasting is kind of garbage. But now we have this x plus alpha blah 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 and this gamma term. And notice that we can, since we're dividing by this, we can just flip this. So now this becomes, if I write equals here, so we're dividing by a fraction. So if you take the reciprocal of this, we can bring it up to the top. And this becomes gamma of n plus alpha plus beta divided by gamma of x plus alpha times gamma of n minus x plus beta times theta to the x plus alpha minus 1 times 1 minus theta to the n minus x plus beta minus 1. Well, do you see something familiar? This is simply just the beta function with x plus alpha and n minus x plus beta. And so now this is the posterior distribution, which we just completely derived by hand. And so you can see intuitively, if I want to update my posterior distribution with new information, I simply just update my alpha parameter with my x's, or in this case of a binomial, this would typically refer to successes, and then I update my beta parameter with my n minus x, or my quote-unquote failures. Because if x represents my successes, then my remaining are my failures. And so if you were to look up the posterior distribution on Wikipedia for a binomial and beta prior, this is exactly what you would get. And of course this in particular represents one sample, but if we were to actually use a joint density for the binomial, this would actually be the sum of x's. So this would be beta, and then we would have the sum of x's plus alpha, and then n minus the sum of x's plus beta. And then we can go one step further and get the posterior predictive distribution, but I might do that another video because this has already taken some time. But hopefully you found this useful and interesting, maybe even shed some light on how to derive these posterior distributions by hand. But of course, in a practical setting, you wouldn't really have to, because you could just use something like R. But I think it's good to know the mathematical foundation of how to actually do these integrals yourself. So, yeah, that's all I have. Thanks for watching, and maybe I'll continue this into the posterior predictive distribution later. See ya.